Yeah, you can start.
Okay, welcome everybody. Welcome everybody. So just a second. So today I would continue with the topology class or geometry. So my job is to explain the second fundamental form. So I will be a little bit slow initially, and initially I would also recall a little bit about what we expected in curve. So let me start then. And please stop me whenever anything is not clear, okay? Okay. So the goal is to measure somehow how curved a surface is. In other words, we are trying to define curvature. So the goal is to measure how curved a surface is. And we will see many different approaches of defining a curvature. So let me just remark. So we would see many different approaches. But interestingly, we would see after the lectures that all the different approaches would somehow lead to the same geometric object, which is the second fundamental form. Okay, so that's the goal somehow. So now last week we have already seen first fundamental form. Right, so this we have already seen. So now, interestingly, this first fundamental form, this is an example of something what is called intrinsic geometry. So it's kind of like whatever how you calculate, it's like an intrinsic property of the surface. And this week we will learn what is second fundamental form. And this is example of extrinsic geometry. So don't bother about these fancy names. I mean, these are nothing. I'm just trying to somehow ease into the definitions. Okay. So what I am trying to say is, once you have sufficient knowledge of this intrinsic and the extrinsic geometry, you should be able to determine the surface. And actually later we would see later one can show that a surface is determined up to some isometry in R3 by its first and second fundamental forms. Okay, so this you should remember. I mean, this similar kind of result we have already seen in the curves section. So like, for example, similar to when a unit speed plane curve, which is determined by its sine curvature, right? This we have seen even, I think, in first week itself, is determined by its sine curvature up to isometry again. So up to isometry, here now in R2, right? I mean, we are considering carving. So what I'm essentially saying, so we already know what is first fundamental form. This week we will learn second fundamental form, and then the idea is these two should determine a surface up to an isometry. Okay, and of course I will, as I said, that there will be different approaches to define the second fundamental form, and interestingly, every approach will lead to the same definition, and some definitions would have more geometric meaning and some with more computational flavor. So today, let me start with some first attempt. So this, I will again mimic the construction of how it happened in case of a unit speed curve. Okay. So if you recall, how was it? I mean, like, how was the curvature of a curve defined, right? I mean, so let me first let gamma in R2 be a unit speed curve. Okay. So now let me consider this curve, and let's say this is gamma t, and I am trying to find out how the curve moves away from its tangent line at gamma t. So let me also consider gamma t plus delta t. So essentially what I am considering here, and this is the unit vector, which is perpendicular to the tangent vector. So this we have already seen. I mean, so what I want to now consider the deviation, like how much the curve essentially moves here to here from its tangent line at gamma t. So, and this is of course given by gamma t plus delta t minus gamma t times the unit vector. I mean, n is the unit vector, which is perpendicular to the tangent line, right? So this is what we have already seen, that this is the deviation in some sense. Now this we can actually expand by Taylor's theorem. So this gives gamma t plus delta t. This is nothing but gamma t. Then you have gamma double prime t plus half t del t square plus some higher order terms. Yeah. So where this higher order terms divided by delta t square, this actually goes to 0 as delta t goes to 0. That's like the basic Taylor series expansion. Right? So that's fine, right? This we have already seen. I mean, so essentially the difference between this and this should be this part and this part essentially. Yeah. Ah, sorry, this should be, yeah, no, that's, yeah. So now, since n as a unit vector, this is perpendicular. So, sorry, as 0, so this implies the difference or the deviation, this should be half comma t times n delta t square plus some higher order terms. And this was the motivation behind, so this gives the magnitude of the definition, the magnitude of the derivation, sorry, of the deviation is half norm of comma double prime t times delta t square, and this gives us the first definition of curvature. So this gave us the first definition of curvature. Let me say this kappa as comma double prime. So this we have already seen. So the idea would be to mimic this construction for what we have seen this in curve. Yeah. So like essentially we would see the deviation between how the curve varies. Instead of now we would see how the surface would vary with respect to some suitable parameterization or in some surface patch. So is this fine? I mean, do you have any questions till now?
No, sir, it's fine.
Okay. Yeah, this we have already seen, right? I mean, this is not, but I just still wanted to recall because sorry, yeah. So just to have things immediately in mind so that we can come back to the surface, what I am now coming to. So now coming back to surface. Okay. So first let sigma in R3 be a surface patch or like a parameterization. Along with some standard unit normal vector, unit normal n. Okay. So now again here I would try to consider similar example as curve. So let me try to draw some surface here. Forgive me for my bad painting. So here let's say this is sigma uv. This is n. Let's say this is sigma u plus delta u, comma v plus delta v. And that's like the tangent plane. So essentially now what's the idea? So we are trying to, so if uv move to u plus delta u comma v plus delta v. So we want to consider sigma u plus v, v plus delta v minus sigma uv. So that's the deviation, right? Now again, similar to curve, what's the distance what the surface moves away from the plane through uv? So it's like parallel to the tangent plane by a distance, then you take the dot product with n, right? N is the normal. It's exactly similar to what we did in case of curve. So essentially deviation is sigma u plus u v plus sigma v minus sigma uv. Okay, that's fine, right? So similar to what we did in the single variable, we had Taylor expansion series expression for single variable. Now we would use the two variable Taylor expansion. So that's the next thing. So we would now use the two variable Taylor expansion. So this would give sigma u plus v plus delta v minus sigma u v is sigma u delta u plus sigma v delta v plus half sigma u u. These notations are all clear, right? This we have already seen. And please stop me if there is some notation I am using which is not clear, okay? But I assume that these notations we have already seen previously. I mean, these are like first derivative and second derivative partially with respect to u and v. So sigma u u delta u square plus sigma v sigma delta v square plus 2 sigma uv delta u delta v and plus some higher order. So essentially here what we are doing, we are expanding along this small like if you take origin or with respect to origin, you somehow have Taylor expansion along this. And in terms, so when we had in the single variable, then it was just a single variable essentially. So here we have a one variable thing. So here one contribution, here one contribution, and then one coming from here, and then you have one contribution for delta v, one for here, and then another one, and then good. So and here also, of course, you have the here as again similar to the single variable Taylor expansion, the higher order terms divided by square plus delta v square. This goes to 0 as delta u square plus delta v square goes to 0. So this is nice because then essentially what does this expression tell you? That it's enough to consider for the deviation, enough to consider only this part. We don't, we ignored the higher order terms essentially. Because in the higher order terms, you will have like the degree 3, degree 4, and mix of everything. So we don't care about those, right? And here also, again, I'm stressing as similar to the single variable case or like the curve case, we know that sigma u, this is if you take dot product with n, this is 0, as same as v. Why? Because the tangent is perpendicular to n, right? So that's nice, because if you remember, oh, sorry, I have somehow. So if you remember now, what was the deviation? The deviation was this difference, what we are expanding in terms of Taylor series, dot with n. And now we have already an expression of this. And this term, this will vanish due to just because of the perpendicular property of the tangents to n or to the unit. It's just by choice. It's the exact same thing happened also in the single variable case. And then if this is true, then what happens? So then the deviation essentially is half. Let me note by L delta U square to M delta U delta V plus N. There is a abuse of notation. This N is not unit normal, but I'm sorry, this is like the notation how it has been defined. So N delta V square. So what is this LMN? So where this L is sigma U with N. Yeah, that's what I was saying. This N is the normal. Yeah, it's a bad notation. I'm sorry for this. Sigma, so M is like sigma U V N, and N is like sigma V V. So this bold N are like is the unit normal vector, and this this small n like without boldness, that's like the notation only. Okay. So it's I have not done anything. I mean, I just rewrote this term actually. Yeah, which is evident from the Taylor series. And I ignored the higher order. So, and ignoring the higher order, which I could do because since if you have delta U square plus delta V square goes to 0, then this goes to 0. The higher order term also goes to 0. Okay, this is nice because then this gives me the first definition. So definition. So let sigma be a surface patch, then the second fundamental form is given by L du square plus 2 times M du dv plus N dv square. So where L, M, and N are, this L, M, and N are essentially defined like this. Okay. And that's the first definition of the second fundamental form. Yeah. And if you now, let me again go back. If you see the curve definition, yeah. So this guy was the curvature, right? So it was exactly similar, half the curvature times the delta t square. And that's what exactly is happening here. Yeah. So half this and times whatever is the deviation here. So let me remark this. So it's analogous to the curvature times delta t square for curve. And you have to just remember, I mean, this is not difficult. L is like the double derivative with respect to u, and then take the dot product with n, and then m, and similarly n. And if you remember again the first fundamental form, the form's expression is kind of similar. Of course, then L and M and N, there it was defined as E, F, and G, right? And it's not clear that it would be equal or not. That's not true. But I'll come later. What we can say about this. So essentially, now we see what's the second fundamental form given a surface patch. So if you are given a surface patch like delta, along with its unit normal, this n, then you can define this L, M, and N with respect to sigma. And then you can define this form L du squared 2m du dv n dv squared, and that's the second fundamental form. Okay, so that's the second one. So any questions?
No, sir.
Okay, perfect. So let's calculate some examples. Yeah? That's like the first thing we should do. So the first example, we'll take an example of a plane, right? And as I was motivating you, or at least trying to motivate you, that this should somehow determine the curvature, right? Or like what intuitively what I am trying to say is, I am trying to find out the deviation from being a plane at each point. So essentially, if we are considering, let's say the next example, what we are going to see, it's about a plane. So what's about the plane? If it's a plane, then the curvature should be what? I mean, any guess?
Zero.
Yeah, exactly. So we have now found some definition, and let's compute the let's say second fundamental form, which should determine the curvature, and then that should give us zero, right? So let's see if it's a reasonable definition. I mean, that's like a way of justification. So let sigma, I mean, the parameterization is like A is a point, U P P Q, where A is a point in plane, and P and Q are two unit vectors. And that are parallel to the plane and perpendicular to each other. So essentially, you get a full parameterization. Okay. So now, if this is the surface patch, let's say, so what is sigma u? So any guess?
P.
Yes. And what is sigma v?
Q.
Yeah. So these are like constant vectors, right?
Yes.
Okay. So once you have sigma u, sigma v, p, so that gives you what is sigma u is then?
Zero.
Yes. And that's exactly same for sigma
UV and sigma VV.
Okay. So if this is the case, then the second fundamental form is also zero, right? I mean, because all the terms are zero. So if you take dot product, it's also. So that's a relief. I mean, that's is also seen. That's good, right? I mean, this somehow tells us that what we have seen, it's not that bad as a definition. I mean, it is measuring how the curve is deviating from the like from being a plane at each point, and since it is a plane, so there is no deviation at all. So okay, that's fine. So let's consider some non-trivial example. So another nice example which you have seen also for first fundamental forms, for calculating first fundamental forms. So let us consider a surface of revolution. Yeah. So you know what is the surface of revolution, right? This you have seen the example. I mean, you take a curve and then around the axis you rotate, and you can find many different examples like cylinder, sphere. Many things are actually special cases of this. And this also, I guess you have already seen, one parameterization of a surface of revolution is sigma uv is fu cos phi, fu sin v, gu, and you can also assume fu is 0 for all u, and the profile cloud given by u sending fu 0 gu, this is actually a unit speed. So in other words, what I am trying to assume is, in other words, f dot square plus g dot square is 1. So that's like the whole assumption, I mean, for one surface of revolution. Okay. I mean, I actually took some nice photos from Wikipedia actually for surface of revolution that I have put in the lecture note. I am not able to draw that such nice thing, but yeah, okay, you could check it out. But the important point is we know the parameterization. So then again, we can then compute sigma u, and this you could check. It's very easy. F dot cos p, f dot sin v, g dot, and then similarly sigma v would be. I hope you are following, right? I mean, sigma,
Yes,
it's
sir.
like just, yeah, I'm just taking the derivatives, nothing complicated. Sin v,
F sin v, F cos v,
yeah, and
0,
yes,
because it is
perfect.
u. So
Yes, yeah, perfect. So then you take the cross product of sigma u, sigma v. Any guess what this would be?
Zero.
Is it? I mean, can you check once more? Hello? Hello?
Yes, sir, you are audible.
yes, sir.
Ah, okay. Yeah, sorry. No, it's not 0. I mean, it's you have to compute.
G dot cos v.
Yeah, minus f g dot cos g, right? Because you have
Oh, okay, okay. Yes.
right. I mean, you take the kind of the determinant of this other adjoint part, right? Yeah. Yeah. So similarly, then for the second factor also you have minus f
Minus
g dot
sin v.
sin v. Yeah. And then for the third part is f f prime. I mean, this is nothing. Yeah. nothing complicated. You can just see. And once you have the sigma u cross sigma v, then the norm of this, using the property of like, since this is true, so this you would find this is nothing but f only. Okay. So this implies the unit normal vector. This is nothing but sigma u cross sigma v. Sigma v. So this is then minus, you just cancel out f, right? Minus g prime cos v minus g dot sine v and f dot. Okay. And so for the fundamental form to be computed, I not only need sigma u, I also need sigma u, sigma uv, and all sorts of things, right? So let's compute those also. It's just computation. I mean, sigma u is again, I mean, I'll write down, don't bother. I'm sure everybody of you will be able to compute this. This is nothing. F double dot cos v, f double dot sine v, g double dot sigma uv is like minus f sine v, f cos v, and 0, and sigma vv is minus f cos v minus f sine v and 0. So finally, this should now give us the L. This is what sigma u dot n. And this also you can compute. This would be like f dot g double dot minus f double dot g dot. M you can compute sigma uv dot n. This will be 0 actually. And n would be sigma vv dot n is f g dot. So this gives us the second fundamental form to be like L is the first coefficient, f g double dot minus f g du square, and then m is 0, right? So m is like the mixed term, du dv is 0, and then finally we have f g dot dv square. So that's the whole expression. Okay. It's that easy. I mean, you can find now many different examples of you can take whenever you have a surface patch, you have a parameterization, you just go through the computation. That's clear, right?
So,
okay. So now one small thing I want to remark actually. I don't know if you recall from last week's lectures. For for this surface, also the first fundamental form was computed, and this was not actually this expression. But let me specialize to another example. Sorry. Let's take this as a third example. So I want to consider the surface unit sphere. So consider the unit sphere S2. So this is a particular case of the surface of revolution, right? So what do I mean by particular case? So you could use actually the same parameterization by substituting, put u equal to theta, v equal to phi, f theta equals to cos theta, and g of theta is sine theta. Yeah. So if you put this, then the second fundamental form from the surface of revolution, what did we compute? This was what? F dot g double dot minus f double dot g dot du square plus f G dot dv square, right? And now if you just compute this, so this, you would see this comes nothing but d theta square plus cos square theta d phi square. Right? I mean, this you can again just compute. I mean, you just substitute all this. Okay? It's clear, right?
Yes, sir.
Yeah. Okay. And now this you should remember. I don't know if you actually remember. For a unit sphere, this was the same as this was also the first fundamental form.
Yes, yes.
So sorry. Yeah, go ahead. You were saying something.
No, sir, nothing.
Yeah. So, but this is the same what we have also seen last week. So, my question for you would be, right? So, question. So, what will be the? So, what is the relation between first and second fundamental form for a general sphere, not a unit sphere necessarily? Yeah. So, any guesses? This you could think later also, but it's not that difficult. I'm just I can ask immediately also. Any guesses and what it could be? This you can think of little bit, right? I maybe later come back again. Yeah, you should see what we have seen already, the base example, right? If it is a unit sphere, then it's the same. So if it's not a unit sphere, then it will have a constant radius, right? So then what can you say about the relation between first and second fundamental? Okay, it's not difficult then. Yes. Good. So I still have at least 15 minutes left, I guess. So let me continue then. So in this section, essentially, let me again summarize. So what we learned is a way to define somehow like an explicit way to determine the curvature, or like here I'm naming this as a second fundamental form. Now, as I promised you that it's not the only way, there would be different ways. So that's actually now the second section. It's about Gauss and Weingarten maps. So it's named after two mathematicians. Okay, so Gauss, of course, everybody knows, but Weingarten is also a German mathematician. Even though sometimes the German names are very funny. Weingarten is it means, literal meaning is garden, wine garden. Yeah, but that's a family name. Anyway, so he was also a quite famous differential geometer in the 19th century. So in the previous section, so what we have seen, how did we define the or describe the curvature? So essentially we looked, so in the previous section, so we looked at how much the surface essentially deviates from being a tangent plane around a point, right? Point on the surface. That was the idea. We just calculated the deviation in terms of Taylor series expansion, and then that gave us the definition immediately of the formula of the second fundamental. Now, if you let me go back to the picture here. So here you see what we check the deviation from here to here about how the surface is deviating. There is one another natural way how one could also see how the surface is deviating. It's by considering how the normal vector is deviating, right? I mean, so similar approach would be how this normal unit vector is deviating. So for example, if it's a plane, and then if you have, let's say, normal unit vector for every plane, then the normal unit vector will be constant, right? So if we can somehow capture the deviation of the normal unit vector, that should also give us an idea about the curvature, correct? It's the same thing, right? I mean, here we are first considering here, or other words, we can also consider for the normal unit. That actually would be the motivating factor behind this. So let me just remark this. So similar approach could be also done by looking at how the unit vector varies. As I was saying, I mean, if it's a constant variation, then of course the curvature should be 0. And if the more the unit normal vector varies, the more curved essentially the curve should be, like the curvature essentially. So here also, let me now try to draw some picture. So let S be a surface, and let me consider different unit normal vectors at different points. These are all n. So for every point, you have a unit normal vector. Now these, if you consider like this, as I have drawn, these are scarce. Like, I mean, the directions are arbitrary anywhere. But if you put all the unit normal vectors from a same origin, like what I'm saying is, so let's say then these will be actually, since the radius is 1, this will be, so this will be a, let me, this sphere, this origin, then this would be all the, right? Somehow this should be defined as a map called Gauss map. So what I'm saying, take arbitrary point, consider the normal unit normal vector at that point, and then consider this as an here as an element in the sphere, okay, as a vector in the sphere essentially. This is the, so let me define this like a proper way. So essentially what I am saying is the values of the unit normal n at points of the surface, these are given by the Gauss map GS, but sometimes if the surface is clear from the notation, you sometimes forget about S. I mean, you just say G. G is the G for Gauss. So essentially what we defined, G from S to the unit sphere S2, sending a point P to the unit normal vector NP, which is like, let me just write this down, unit normal S. So that's exactly the map. I mean, this is the map essentially. You take any point, then consider the unit normal at that point, and then consider as an element in the sphere. Okay? It's clear, right? I mean, this is not that complicated. It's like almost immediate actually. So now, sorry. So what's our motive? Aim? Our aim is to measure how the surface is curved. And how did I say that in this section what we are trying to see? We are trying to see the variation of the unit normal. So essentially what I'm saying, we want to, so aim to observe how the normal vector n changes around a point, or like a vary. So how do we determine how a vector changes around a point? By considering its derivative, right? I mean, and that's exactly what we would consider, like, and will be given by the derivative of the Gauss map. And actually this map will be defined, which I am going to define again in the next page itself, is called Weingarten map. Okay, so let me define this then. So first, I mean, so till this, okay, right? So we will consider the derivative of this Gauss map, but let's first consider some few more remarks. So what I'm saying, we are going to consider the rate at which n varies across the surface. So this is given by, of course, the derivative d at the point P of G. And you know what's the derivative for a point, then it becomes the tangent plane, right? So from TPS to TGP S2. Right? So for P, you go to GP, and then GP is an element in S2, and at that element you consider the tangent plane. Right? Now, one interesting thing to note before I come to the formal definition, and then I will stop for today. So note that given a point P in S, the tangent plane of GP at S2 is actually equal to TPS. So that actually we can see by simple consideration, because what is TGP of S2? So this is what? This would be like, by definition, this would be like the plane through the origin and which is perpendicular to NP, right? That's by definition. I mean, but then this is again, that's exactly what TPS is also. So that's not, I mean, if you remember let me again come back to here. I mean, this NP is essentially this NP. So it's not that surprising. I mean, so essentially, this I'm not saying much deep thing. I mean, this is quite obvious actually. But then if this is true, that's very nice because now I can replace the right-hand side by also TPS. So let me conclude then in this page. So then we have the dP of the Gauss map is a linear map from the tangent plane TPS to TPS, right? And that's exactly what we are going to now define in the Weingarten map. So definition. So let P be a point of a surface S, then the Weingarten map W at the point P of the surface S, so at P is defined by the following. So WPS is minus dP. Why do we give the minus? I mean, it's actually the minus sign is a matter of convenience, and later actually you would realize that it saves us from many different minus signs. So the minus sign kind of is a matter of convenience. And helps in calculation later. Helps in later calculation. Okay, so I have 2 more minutes. So let me just then in 2 minutes give the second definition of the second fundamental form. I mean the second definition of the second fundamental form, and then tomorrow I'll continue with the properties of this. So once we have the Weingarten map, then the second fundamental form of S at the point P in S is given by the bilinear form on tangent plane TPS by VWPS is WPS V WPS for all VW in tangent. Okay, so you define a bilinear form like inner product using the map here. And why this is valid? Because WPSV now is an element in TPS, right? Because that's minus DPG. DPG is a map from TPS to TPS, and this is also an element in TPS. And on TPS, we know the inner product. So this is that inner product. And that's the definition of the second fundamental form using the Weingarten map. Okay. So now there are many questions left. Of course, we need to prove this is a bilinear form. And then the next obvious question what you should ask, whether this definition is coherent with the definition what we saw from the first section. Yeah? And those all things we will see in the next. Okay, I'd stop here. Any questions, please?
No, sir.
No, sir.
Okay, yeah. Okay, then I'll stop sharing. Yeah?